In this lecture, we'll be uh, discussing how we can design feedback lineation-based control for the system which cannot be defined in the standard form x dot equal to ax plus bu gamma x into u minus alpha x. As you have done in the last lecture, that if the system, if you can write in this form, we can design the state feedback lineation-based control. But if you can't in this form, then how we can design the control for that system? So let's take an example how we can tackle this problem. Following system, x1 dot equal to a sine x2 and x2 dot equal to minus x1 squared plus u. And here our motivation is how we can design the control u, which is going to control the states x1 and x2. So here, if you notice here carefully, this cannot be represented, the system cannot be represented in this form. It is difficult. So how to tackle this kind of system if you have? So now we can solve this problem using feedback lineation-based control. So if you consider the following state transformation, like if you consider, let us apply the state transformation as we are defining new variable z1 equal to x1 and z2 equal to a sine x2. So we are defining two variables z1, z2, which are basically function of x1, x2, right? So from this transformation, we can write z1 dot equal to x1 dot, which is nothing but z2, and also we can write this one as a sine x2. And z2 dot we can define as a cos x2 and x2 dot. And from this we can write a cos x2, and in place of x2 dot we can write, from this expression we can write u minus x1 square, right? Now in this system equation 3, now we can define in this form. So how we can define? Let's see. So now we can write z1, or we can write the equation 3 can be represented as equation 1. We can write z1 dot, z2 dot, we can write z dot. So here 0, 1, 0, 0 into z1, z2 plus 0, 1 a cos x2 into u minus x1 square. So here, this is my A matrix. This is G vector. This is B. This is gamma. And this is alpha x. This is gamma x, this term. So now the control, as we have done in the last lecture, the control law can be defined as, if you can represent the system, this system, in this form, then we can design the control for this system. So here we can write E equal to alpha x plus beta x into V. So alpha x, if you notice here, actually it is x1 square, and beta x, we can write gamma inverse x. So it is basically 1 by A cos x2 into V. So this is the control U, which is basically nonlinear control. But if you substitute this this U in this expression, so we can write the system into linear form. So how can do it? So let us define, this is equation 4. This is equation 5. Now substituting equation 5 in equation 4, we are having, we can write Z1 dot equal to Z2 and Z2 dot equal to V. Simply you can write this expression. So if you substitute this expression, you can try. If you substitute this expression, U, in this expression, we can have this form. So this is basically a linear system, and we can design the control for V, which is going to control G2, and this G2 going to control G1. So now, if you choose, now let V equal to minus Kg. This is what we have learned in the modern control. We can write K1 G1 minus K2 G2. So if you substitute this B here, if you substitute this B here, so we can write the augmented system. We can write Z dot equal to, we can write 0, 1 minus K1 minus K2. This is our closed loop system. So here we can have the DGR dynamics, what I have done in the modern control, DGR dynamics, and we can compare the characteristic equation 0, 1 minus K1 minus K2 equal to 0. And we can compare both the equation, and we can find the value of K1 and K2. So we can design the control for this system. Now we can find the value of U, which is going to control the overall system, the system. So now U can be defined as the control, the nonlinear control U for the system, equation 2, we can write E equal to, we can write x1 square plus 1 upon A cos x2 into V. So V is nothing but our DGR dynamics, which is, this is the V expression. Sorry, this is the control for Z dynamics. So we can write minus K1 G1 minus K2 G2. So here we can write, x1 squared plus 1 upon A cos x2 into minus K1. So G1 actually we have x1. So this is x1 and K2, and G2 we can denote A sine x2. A sine x2. So this is the nonlinear control. This is the nonlinear control which is going to control this system defined by equation 2. So this is how we can use feedback linearization to design the control for the nonlinear system. This is very simplest method in nonlinear control techniques. Now we'll be taking how we can design the feedback linearization for the system. So there are two types of feedback linearization basically. So the feedback linearization are two types. One is full state linearization, and second is input output linearization. The full state linearization actually we have done. So whatever stuff we have covered in the previous lecture and in this lecture as of now, these are actually part of the full state linearization because we are using the full state in designing control. So here we are going to start the input-output linearization, how we can design the input-output linearization for the system. So we'll be taking an example of the aircraft system and how we can apply this concept for the system. So let's take an example. So it will be easy to understand if you have example. So let's consider we have example. The pitch dynamics of an aircraft can be modeled as theta dot equal to omega and omega dot equal to f theta omega plus z theta omega into u. So we are considering some general equation for the pitch dynamics of the aircraft, and here we'll be designing the control for this system. So let's consider this the pitch dynamics of the aircraft. So here theta is the pitch angle and omega is the pitch rate and u is the elevated deflection, which is basically control input, or this is also elevated deflection, which is controlling the pitch angle of the aircraft, and f theta w, this is, we are assuming this is the nonlinear aerodynamics forces and moments, and z theta w, we are assuming control coefficients. So now we are going to design the control u, this control u, which is going to control the theta only. So how we can control the pitch angle of this system. Okay. So our control objective is design a control u which helps theta to track theta desired theta, the desired theta t, or you can say trajectory. This is a very interesting problem. How can design a control for the system which can help to track the desired trajectory of the system. So this is our control objective for this example. So we'll start solving this problem using the input-output linearization here. This concept will apply here. So here, let us define our error function E equal to theta minus theta desired. So in this case, the goal is E tends to 0 as t tends to infinity. When E tends to 0, it means when theta desired goes to theta or theta goes to theta d, right? When error goes to 0, so this part going to 0. So here we can assume theta desired can be tracked. So here, before proceed to this problem, we need to understand some important topic in this case. So here, one concept we have to discuss here, concept. Since we are going to use this method, so here we need to come up some rule which can help us for designing the control. The number of times the error equation and the number of times the error equation E of t, which is actually given E of t, let's assume this is the E of t error, must be differentiated before the control input appears in the error dynamics. So here the thing is we have to take the derivative of this expression till we get the control input in this dynamics. Okay. So here, if you notice here, okay, let me write. Here we are taking the output equation here. We are taking the output equation as a, or you can write to find the control. So from the title of the concept, input-output linearization, so here we're going to take the output equation, and that output equation will differentiate till we get the control expression in the output equation. Okay, so here, since we have the error equation here, we have defined here. So let's take E of t equal to theta minus theta d. So if you take the first derivative of E of t, we can write theta d minus theta dot minus theta d dot. Or you can write theta dot, we already have omega. So you can write omega minus theta d dot, right? So in this expression, if you notice here, the control is not appeared, right? So you can write control is not appeared. So now we have to take again the time derivative. So E dot double dot of t, we can write theta double dot minus theta d dot. So here we can write, in place of theta double d, we can write omega dot minus theta d double dot. So now it is clear that, so it's double dot actually. So it is clear that omega dot is appeared in aerodynamics, and omega dot actually also function of control. So we can write here, this is a very easy process to design the control. If theta omega plus z theta omega u minus theta d double dot. So you can see that control is appear. So here, what you're gonna do is to linearize the system, to linearize the system, what we're gonna do is we are taking E double dot of t, we are assuming this is as a v. So this is we are assuming to make to design v in such a way that over time e of t is going to 0. So what you're gonna do is, so this is basically nothing but the linear system. So we can write here, this is the aerodynamics. The aerodynamics is linear. Yeah, the aerodynamics is linear. So now let's design the control input for v so that e of t is stabilized. Yeah. So here we are assuming this is also can transform into the similar step, the step what you have followed in the last lecture, the same steps you can follow. So here you can consider e of t equal to x1 and e dot t of equal to x1 dot equal to x2. You can write x1 dot equal to x2 and x2 dot equal to, you can write b. This you also can write, right, from this equation 1. So now we are defining the control for this dynamics, the control. Let's consider the control v equal to minus k1 e and minus k2 e dot. This is also you can write in this, if you consider this expression, this system, so it will be something minus k1 x1 minus k2 x2. The same, it is up to us how we can proceed for designing control for the system. So if you notice here, so here if you have v, this v, if you substitute in the system, our system will be stable system. How? Because if you notice, if you write here, if you substitute this, let us define this the equation 2, substituting equation 2 in equation 1, we can write e double dot t equal to minus k1 e minus k2 e dot, or we can write e double dot of t plus k2 e dot plus k1 e equal to 0. So here actually k2 and k1 are positive. So in this case, this system is stable system, right? So over time, e of t goes to 0. So this is basically stable system, right? So now what you're gonna do is we'll substitute this v here. We can substitute this v here, this v, the expression of v here. This is also v because e double dot t we have assumed to be v. So this is also v equal to this whole expression. So now we can write the contour for the system. Let us define, okay, this should be, let us define now star. Okay. The contour for star, we can write v equal to, we can write this full expression here. This expression here we can write, right? So let me copy it. This. So from this we can write or we can write u equal to, we can write 1 upon g theta w minus f theta w plus theta dz double dot minus k1 e minus k2 e dot. This is what we can write. Or we can write 1 upon g theta u minus f theta w plus theta d double dot minus k1. We have the e theta minus theta d, and minus k2 theta dot minus theta d dot. So this is our control expression for our pitch dynamic system, for this system. So this is how we can design the nonlinear control for the nonlinear system using input-output linearization. So this is very, very powerful technique, how we can design a control for the nonlinear system using this concept. Let's stop it here. We'll have another aircraft example in the next lecture, and then we'll wind up this concept. Thank you.